We all know what sound is, right? It's sound. We hear it every day, obviously. But, and I don't know about you, but I don't often think about how it actually works.
Yeah, it's one of those things like you know it's there, but the actual physics of it, easy to overlook.
Exactly. But that's what makes today's deep dive so fascinating. We're exploring sound using, get this, excerpts from the Feynman Lectures on Physics.
Oh, Feynman, always a treat. The man had a knack for taking the most complex topics and making them not just understandable, but exciting.
Right. So what's the angle here? Why do you choose sound to illustrate these, what was it, wave mechanics?
Good point. It's interesting because, yeah, light's a wave too, but sound, it's ultimately about mechanics, like literally air molecules bumping into each other.
Hold on. So it's like a billion tiny billiard balls colliding to make music.
Pretty much. Though maybe not billiards exactly, more chaotic. But before we get too carried away, it's important to set the stage here. Feynman's mainly interested in what happens between a sound source, your voice, a trumpet, whatever, and where it's heard, someone's ear.
Makes sense. So like the journey of the sound wave.
Exactly. And to keep things manageable, we're assuming distances larger than a molecule's mean free path.
Mean free path. Okay, now that sounds kind of menacing.
Less dramatic than it sounds, I promise. It's just the average distance a molecule travels before it bumps into another one.
Got it. So we're going for a big picture view of sound waves, not zooming in on each molecule. Okay, so how does Feynman break this whole thing down?
He identifies these three core concepts, like the foundational pillars of sound. First up, density and displacement.
Okay, density I get, but displacement. We talking earthquakes here, or?
Not quite. Think of it this way. How tightly packed those air molecules are, that's density.
Hmm.
Displacement is how they move around. Like imagine a crowded room. Everyone shuffles a bit. You've got displacement. The density of the room changes slightly.
Ah, okay, I see. And with sound, those density changes are happening constantly because of those, what did you call them, those tiny molecular collisions.
You got it. And you can't talk about density changes without mentioning pressure. That's our second pillar.
Right, because the more crowded those molecules are.
The more they bump into each other, creating higher pressure, less crowded, lower pressure, direct link.
Makes sense. Although we're talking tiny pressure changes here, right? Like what's the difference between, say, a whisper and just, I don't know, the air existing?
Huge difference in scale. Even a loud sound, like 60 decibels, that pressure change is a tiny fraction of a percent compared to just the atmosphere, the air pressure we live with.
Wow, okay. So our ears are picking up on these minuscule shifts. Wild. But how did that actually make the sound wave? Where's the motion come in?
That's the third pillar, and this is where it gets really interesting. Those tiny pressure differences we've been talking about, they're the driving force behind the movement of the air molecules.
So it's like a domino effect. Or wait, is it more like?
It's a chain reaction for sure. Those pressure variations are like a billion microscopic dominoes all setting each other off. That chain reaction, that wave propagation, that's what Feynman describes with what we call the wave equation.
Equations. Now we're talking serious physics. But before we go there, remind me, why is this wave equation so important? What's it actually tell us?
The beauty is, it's not just some formula we accept blindly. Feynman shows us how we can derive it from basic physics, force, mass, acceleration. And by applying those to sound, the math shows us that disturbances in the air will travel at a constant speed.
And that speed is... Don't leave me hanging.
Well, the equation itself doesn't give us an exact number, at least not yet, but it does something even cooler. It shows the relationship between that speed, the speed of sound, the pressure changes we talked about, and the density of the air. And that's where things get really wild.
Okay, so we've got this wave equation, right? And it connects the speed of sound to pressure changes and, what was it again, air density? But how do we actually put those pieces together? Like, give me the equation to calculate that speed. I'm ready.
You're always ready for the formula. But remember, the fun isn't just in the answer itself. Feynman wants us to understand where it comes from.
Okay, fair enough. Walk me through it. What are the ingredients in this speed of sound recipe?
All right, imagine a balloon. You squeeze it, pressure goes up inside, right?
Right, makes sense.
But how much it goes up, that depends on how, I don't know, resistant the balloon is to being squeezed.
Ooh, okay, so like a super stiff balloon, that'd be harder to squeeze. Smaller pressure change. But a flimsy one, whoosh, big pressure change.
Exactly. And it turns out air, or any medium sound travels through, it has its own resistance to being squeezed. We call that its compressibility.
Catchy. So more compressible means faster sound. Like those pressure waves, they just zip through easier.
You're on a roll. But here's the thing. When scientists first tried to calculate the speed of sound using this, Their answer was off. Way off.
Wait, seriously, how is that even possible? We're talking like basic physics here, right?
Well, they made an assumption. Seemed reasonable at the time. They figured that when sound waves compressed the air, the heat generated would instantly even out. Warmer compressed air, cooler expanded air nearby, boom, even out. Constant temperature.
I mean, that makes sense to me. Heat spreads out, right? So what's wrong with that?
It's about speed. Sound travels way too fast for that heat transfer to actually happen. Imagine trying to stir your coffee, but like one molecule at a time.
Yeah, good luck with that. Okay, so sound is impatient. It's zipping along too quickly for heat to even catch a ride. But why does that matter for the calculation?
Because temperature affects how things expand and contract.
Right.
Heat something up, it wants to expand more pressure. Cool it down, the opposite. So by assuming this constant temperature, when really there are these tiny fluctuations, they were using the wrong numbers.
It's like trying to bake a cake but using the wrong oven temperature. Disaster.
Exactly. And you know who figured that out? Laplace. Factored in the what we call the adiabatic nature of sound, basically no heat flow during those rapid compressions and expansions, tweaked the formula, and bam, the numbers matched up.
The more you learn about this stuff, the more you realize even the geniuses got things wrong sometimes. Okay, so we've got the speed of sound. We know how to calculate it. What's next? What other sonic secrets are you hiding?
Now we get to the really mind-blowing part. Think about what that speed, that number, actually represents.
I'll be honest, I've never really thought about it that deeply. Sound travels at, what is it, like 767 miles per hour? Cool. Moving on.
Hold on. That speed, that's directly related to the average speed of those air molecules bouncing around you right now.
Hold up. Seriously. You're telling me those tiny molecules are slamming into my eardrums at hundreds of miles an hour?
Maybe not hundreds, but yeah. It's not just that the wave is moving that fast, it's that the individual molecules are, on average, zipping around at insane speeds. And all those trillions of tiny collisions every second, that's what our brains interpret as sound. Isn't that wild?
I don't know about you, but my brain's still stuck on the fact that those tiny molecules are just zipping around like that.
Yeah.
Wild.
It really makes you appreciate the elegance of physics, though, right? I mean, we think of it as this abstract thing, but it's dictating literally everything around us, even something as seemingly simple as sound.
Totally. It makes you wonder, what would happen if we could change the speed of sound? Like, what if those air molecules were moving way faster or even slower? What would that world sound like?
Now, that is a fascinating thought experiment. Let's say, hypothetically, we've got this knob, and we can crank it up to make those molecules go nuts or dial it down to a snail's pace.
Okay, I'm picturing it. So crank it up, those pressure waves, they'd be like zoom. Super fast communication.
Right. Imagine concerts. Over in a flash. Unless composers wrote music specifically for supersonic sound.
And don't even get me started on conversations. You'd have to be like an optioneer just to keep up. But what about the opposite? Slowed down. What happens then?
Think about echoes. They'd take way longer to come back. Super disorienting. Imagine shouting across a canyon and waiting and waiting.
Whoa, yeah. Our sense of distance, of space, it's all calibrated to this, delicate balance, isn't it?
Exactly. Mess with the speed and suddenly everything's out of whack. It really highlights how amazing our hearing is. Our brains just take this for granted, but we're processing these incredibly complex patterns of pressure waves, turning them into meaningful sound.
It's like once you start to really see the physics behind
Mm.
everyday things, it's just mind-blowing. It makes you appreciate the world in a whole new way.
Couldn't have said it better myself. And on that note, dear listener, we'll leave you with one final thought to ponder. We've talked about how changing the speed of sound could change how we understand space, even communication. But what about time? If we could manipulate the very speed of sound, would it change how we perceive the flow of time itself? Something to think about until our next deep dive.